Humans naturally integrate sight, sound, and touch into a single understanding of an event. For machine learning algorithms, however, merging these heterogeneous perceptual channels, like high-resolution images and noisy text, presents a severe bottleneck. This process follows a Markov chain. Raw inputs x1 and x2 form latent representations z1 and z2 to predict target y. These inputs decompose into a shared factor, redundant overlap like in animals' identity, and modality-unique factors, capturing independent nuances, like specific bark pitch or fur color. Monolithic architectures collapse all this varied information into a single uniform embedding. They lack a structural mechanism to decide what to align, keep, and discard. Without explicit isolation of these factors, the model passes a chaotic mix of signals and noise to the predictor, guaranteeing suboptimal downstream performance. Most multimodal representation learning defaults to one of two industry paradigms. The first is contrastive learning. This visual represents the contrastive objective's theoretical optimum, aligning modalities by maximizing mutual information. Because this relies entirely on the shared factor, there's zero mathematical incentive to preserve modality-unique features. The encoder systematically strips them away. According to the data processing inequality, once information is lost during encoding, it cannot be recovered. If your downstream target depends on those unique cues, the predictor will fail. To correct this loss of information, recent models employ the second dominant paradigm, Infomax. Infomax aims to preserve everything, successfully capturing both shared and modality-unique factors. But its objective simultaneously maximizes task-relevant and task-irrelevant information. This forces the model to retain a massive amount of redundant noise. Contrastive encoders guarantee information loss, while Infomax models guarantee noise bloat. Neither approach optimizes latent space. To find a solution, we have to define what a mathematically perfect representation actually requires. It must balance two absolute constraints: task sufficiency and information minimality. This equation defines task sufficiency. The representation must capture every piece of data relevant to the downstream target y. And the second equation defines information minimality. It must actively exclude all irrelevant data. A single, fixed embedding simply does not have the structural fluidity to adapt to these dual constraints across varying samples. Instead of monolithic alignment, the system needs distributional semantic coherence. We must break the latent space down into discrete, concept-specific subspaces that can be selectively targeted. Achieving the InfoMen optimum requires explicitly structuring the latent representation as a collection of selectable semantic components, rather than forcing a uniform blend. This structural decomposition is the basis of a framework called S3, Specialization, Selection, and Sparsification. S3 rethinks the mixture of experts architecture. Instead of just scaling compute, it uses experts as a physical routing mechanism to structurally divide the latent space. In the first stage, specialization, the framework decomposes the raw multimodal signal into concept-level experts. Each expert in the network acts as a specialized container, claiming a distinct concept and establishing a strict boundary within the shared latent space. These concept-specific subspaces populate the model, establishing a wide semantic basis for alignment. By binding alignment to these specific, consistent experts, the architecture absorbs cross-modal asymmetry while preserving the strict boundaries between different semantic concepts. Once the space is structured, the framework moves to the second stage, selection. A dynamic routing mechanism adapts to the specific demands of the target task. This chart shows the output from the router. It calculates a probability distribution across the entire network, identifying and activating only the specific expert pathways required for the sample. By physically separating the semantic concepts, the S3 architecture guarantees that task-relevant signals are extracted, while irrelevant data remains dormant in unselected experts. The framework concludes with a final refinement phase, Sparsification. This step executes entirely at inference time. The model tightens its representations without requiring a single additional pass of training data. It analyzes the output distribution generated by the router, evaluating the utility of each active pathway. The system then dynamically prunes the lowest probability paths, collapsing the low-utility experts to zero. This pruning directly addresses the failure of the Infomax paradigm. Sparsification is the physical act of deleting the conditional, task-irrelevant noise from the representation. By severing low utility paths, the model satisfies the information minimal requirement, retaining only what is strictly necessary. A bloated, noisy probability distribution is systematically carved down into a compact, task-focused representation. The efficacy of this structural approach is validated across 4 distinct multi-bench benchmarks. We can visualize this validation by mapping the level of induced sparsity against the model's overall downstream accuracy. Across all empirical tests, the sparsification process yields a highly predictable, reverse U-shaped performance curve. At lowest levels of sparsity, the model allows too much task-irrelevant noise through the active pathways, degrading accuracy. At extreme levels of sparsity, pruning becomes overly aggressive. The model destroys essential modality-unique signals, and accuracy drops sharply. The peak performance consistently aligns at an intermediate sparsity level. This specific coordinate represents the mathematical optimum, where irrelevant noise is suppressed and critical task signals are perfectly preserved. Treating latent spaces as monolithic blocks is a structural dead end. True optimization requires decomposing multimodal data into selectable semantic components. Wielding mixture of experts as a structural inductive bias, the S3 framework successfully navigates representation learning trade-offs, delivering a mathematically principled path to task-sufficient and information-minimal AI.